So today we are going to do this probability lecture 4. I have started this lecture last time. We did um, half of this lecture last week. So the next half is we will be doing it today. But I can repeat because today we are going to study the Bayes rule. But this law of total probability is a prerequisite for Bayes rule. So for Bayes rule, you need this law. So I can revisit this law and then I go to the Bayes rule. So where I can erase this. Is this the eraser? Okay, so uh, these events are called mutually exclusive and exhaustive events. If you take the union of all these events, you see this outside rectangle is your sample space S, right? So if you take these events A1, A2, A3, A4, if you just take the union, it will give you the whole sample space. So see here, so when the union of some events gives you the sample space, we call them exhaustive events. And if I pick any two events from here, their intersection is empty. You see, if I pick A1 with A2, A1 with A3, A2 with A3, so on, all of them have no points in common. So their intersections are empty. They are called mutually exclusive. So these events are both exhaustive as well as mutually exclusive. So we can also call it a partition of the set S. You see, A1, A2 up to AK, they make a partition of a set S because we have partitioned our sample space uh, into these sets which are mutually exclusive and exhaustive. Any set of events who are mutually exclusive as well as exhaustive, they are called the partition of a sample space. Okay, so if you have this partition, so let's consider a simple problem first, where we have only three events. So let's say A1, A2, A3 are mutually exclusive and exhaustive. You see, if I take the union of all these events, it gives me the complete sample space. And if I pick any two events, there is no point in common. Intersection is empty. Intersection is empty here, right? On these three events, let's say B is any event defined on the sample space. This B is any event defined on a sample space, this elliptical event. If we have, if we see this B in terms of A1, A2, A3, then this portion is your A1 intersection with B. And then this portion is A2 intersection with B. And the third portion is this one where A3 and B intersect. So this is the common portion of B with A1, B with A2, and B with A3. So note that this event B comprises of three mutually exclusive events, A1 intersection B, A2 intersection B, and A3 intersection B. They are not exhaustive. They are only mutually exclusive. Okay. We want to basically use the addition law of probability. So you see, if I want to find the probability of B is the union of all these, this event or this event or this event. So whenever B occurs, one of these events will definitely occur, right? Either A1 intersection B or A2 intersection B or A3 intersection B. We had a law for A or B that we add the probabilities of A, B, and then we subtract the probability of AND. We know that this AND is zero in our case because when the events are mutually exclusive, there is no intersection. So they cannot occur together. So it means my law will become only this one. So this is the law I used here. Probability of first event or second event or third event. And because they have no intersection, so no need to subtract anything. We are not subtracting anything. Everything is zero there. Okay. So now because I do not have A1 and B, so my given probabilities here are, because a partition A1, A2, A3 are given, so I am given their probabilities. Probabilities of AI are given, A1, A2, A3, and also the probability of B given AI are also known. Means if I don't know what is the probability of B, but if you tell me which event has occurred, then I can tell you the probability of B. So these 6 probabilities are given to me. Probability of A1, A2, A3 are given, and B given A1, B given A2, B given A3. These 3 events are also given. So we can write these probability in terms of this. So if you recall, what was the probability of B given AI? It was probability of AI and B divided by probability of AI. So if I multiply this on the right hand side, you will get probability of B given A into probability of A is equal to A intersection B. So this is what I used here. You see, this one we use here. Probability of A1 given B, A1 intersection B will become B given A1 into A1. So if we have A2 here, then we have A2 here. If A3 is here, then A3 is here. So intersection probability can be written as probability of B given A1 into A1, probability of B given A2 into A2, and so on. So this is the law of total probability. When 3 A1, A2, A3, these 3 events are given. If you have 4 events, A1, A2, A3, A4, I will have another term for 4. If only 2 events are given, I will stop here, right? So if at least 2 events will definitely be given. So this is just the law of total probability. That's what we did last time in class. So see, this is for now any number of events AK. So if you have 2 events, you will stop at 2. If you have 3 events, you will stop at 3. If you have 10 events, you will go up till 10. B given A10 into P of AK10 and so on. So these 2 examples we did in class, but because I have to redo it for Bayes law, so it's better if I just go to Bayes law now, and you will see how the law of total probability is also used here. Okay, simply remember that what was given was probability of A1, A2, A3, right? And if there is an event B here, right, probability of B given AI were also given, right? So these 6 probabilities are given to me. If they ask you the probability of this event B, if they ask you what is the probability of B in terms of these 2 given conditions, this is the law of total probability that I just did in the previous slide. If they ask, this is given, but if they ask the opposite, that what is the probability of AI given B? If they swap them, right? You see, A1 goes there, B comes down. If they ask this question, then we use Bayes rule. It is the name of someone, so Bayes should be capital. Bayes rule. Or Bayes law, Bayes rule, same thing. Okay, so this is the Bayes rule basically when they ask you the opposite thing. So this is a new one now, and you know that if I write probability of AI given B, it is probability of AI and B divided by B, right? And then I can write this B intersection AI as probability of B given AI into probability of AI divided by B. So see, in the denominator, I need the probability of B, which comes from law of total probability. See, that comes from law of total probability. So within the Bayes rule, I need law of total probability, both of them. So let's go to this one. See, it is the same scenario that we had before, that B is any event and B will intersect with A1, A2, A3, right? So you got three events, A1 and B, A2 and B, A3 and B. Now they are asking, we assume that the probabilities of A1, A2, A3, B given A1, B given A2, B given A3 are already known. As I wrote in the last slide, you can see here, right? So probability of AIs and probability of B given AIs, they are all known to me. And now we want to determine the opposite. You see, the given was B given AI. This is known to me, but now they are asking the opposite. They are asking me A1 given B, A1 given B, A2 given B, A3 given B. So whenever they ask you this one, you have to use the Bayes law. So if I write Bayes law now, as I wrote before, the Bayes law has become this one. You see, probability, if you are doing anything, if you can write it for all, not just for one. So you see in the bottom, this probability of B, the blue one, this blue one is the law of total probability, right? So this one is the law of total probability. So we still need the law of total probability within the Bayes rule. So this is now the general rule for any number of events. So if you have any number of events, A1, A2, A3, though they don't have to be straight lines, they can be anything, right? So A1, A2, A3, A4, so on up to AK. So there are many events, but they are both mutually exclusive and exhaustive. So basically, they give you a partition of the sample space S. Okay, so they give you a partition of the sample spaces. Now you are defining any other event on top of this one. This is your event B, right? So B will have intersection with A1, with A2, with A3, with A4, with A5, and so on. So if you are asking any of them, you see, probability of any of AI given B. So I can be anything here. I can be 1, I can be 2, I can be 3. So how to remember this Bayes rule? Remembering is this one. Go to the top, change it. You see, I don't know what is AI given B, but I know B given AI. So I change it to B given AI, swap it. And then whenever you change, multiply the given probability A1 and divide it by the probability of B, which comes from the total probability. So in short, you can write like this. Probability of AI given B is equal to, change it, because I know probability of B given AI. I know that once I do, I will multiply it by A and divide by, from the definition of conditional probability, this given probability comes down, right? And this B comes from, probability of B comes from the law of total probability, which is B given AI into AI, and we take the sum of all I. We take the sum of all I, which is written here in the denominator. Okay, A1, A2, A3 up to AK. So it's better if you do it separate. You can calculate this separately, right? And put the answer here. Calculate separately and put the answer in the denominator. That will be easier. So let's see an example here. According to an opinion dynamics poll published in USA Today. USA Today is a newspaper in USA. Roughly 54% of US men and 33% of US women believe in aliens, believe in extraterrestrial aliens. Terrest is something which is used for our Earth, right? Terrest, right? Terrest means from this world, right? Our Earth, from this world, or where we are living in, right? And celeste is used for not from here, means skies, right? Space, air or space or whatever you say, okay? A celestial object is not on the earth, it's above the horizon, right? So when they say extraterrestrial, extraterrestrial means not from our world, not from this earth. So there may be some aliens which are not from our world. Sometimes they show these aliens in movies, right? So according to a survey, 54% of the men believe that there are aliens and 33% of women believe that they are aliens. Okay, so let's say if I call, if I use M for men, if I use M for men, then you know that the whole population is divided into only two, men and women, right? So it means these men and women are my partition. So this set is my A1 and A2. This gives me the partition because there is no point in common. If someone is a man, he will not be a woman. If someone is a woman, he will not be a man. So M union W gives me the complete sample space. And if I take the intersection, it's empty, right? So this means it is a partition, right? It is a partition. Now, both some both of them, some percentage of men and some percentage of women believe in aliens, extraterrestrial aliens. So I can call E for that. Let's say M for men. I can use W for women, right? And E for extraterrestrial alien. So he said a US adult is selected at random. What is the probability that that adult that we selected believes in such aliens? So in A, they are asking me what is the probability of E. So you see, this is my event E, which is defined on both the events M and W. It means I need the law of total probability. Probability of E given M into probability of M plus E given women into probability of women. So see, you don't need to remember the formula. You just have to remember the idea. What is the idea? E with M. So E given M into M and E given W into W. You see? E given M into M, E given W into W, and there is no third partition. There is no third set in the partition. Otherwise, I will add that third set as well. But now it's not there. So what are these probabilities? Uh, First of all, E given M. You see here, he said 54% people believed in aliens, but who? Men. So if you tell me the selected person is a man, then I know that he will believe in aliens is 0.54. And 33% of US women. So this tells you that if you tell me that the selected person is a woman, then she believes in aliens is 0.33. So these two probabilities are given. And now I need the probability of the partition, man and women. So here, set of US adults, roughly 48% are men and 52% are women. So this probability is probability of man. Being a man is 48 and there are 52% women. So it means being a woman is 0.52. So now you see all the probabilities have been known to me. I can put it here. This first probability is 0.54 into 0.5248. This is 0.54 and this is 0.48. Then this is 0.33 and women are 0.52. So if I replace all these values, I will get the probability of E. Then what is the probability that the adult is a woman? The adult is a woman given that she believes in aliens. So in B part, they are asking me what is the probability that the adult selected is a woman given that she believes in aliens. So see, they gave me this is the given probability and opposite to this, they ask me the opposite. So the question is the opposite, W given E. It means I need Bayes rule. So what do? I change it. I change it back to what is known to me, E given W. But then I multiply by this given one, the W1, right? But then we divide by this denominator, E. And we have already found this E in part A, you see. So even if they do not ask me part A, I have to calculate part A because my Bayes rule requires that in my denominator. Okay. So now if you use these probabilities, you will get the answer. So you have to understand the problem carefully, read it. So see now, he said let M be the selected adult is a man, W for woman, and E for that extraterrestrial aliens. You can also use A for that, A for aliens, right? But maybe they wrote the full name, so we can pick the first one, right? So for men, we picked M, for women, we picked W, and for this, we picked E. So now probability of men is given in the question, women, E given men, E given W was given. So in first one, we use law of total probability. So I can write that here. This is the law of total probability. That is the first part of this lecture. And then here we use the Bayes law, because what is given, E given M, E given W. If they ask me any of these opposite, right, then I have to use the Bayes rule for that. So this is your Bayes. Bayes rule or Bayes law, both are the same thing, no problem. All right. So you don't need to write this. You can directly write this formula, because we know that W given E is E given W into W divided by E, and E will come from here. E will come from the first, is it 0.4308? 0.4308. So that comes from your first question. All right. Let's read another one. This is the solved example. Both are solved, so maybe I can do. Okay, let's see this one. Example is the first two columns provide an age distribution for adults. Adults, right? Adults are above 18 years. So the third column gives the percentage of the people in age in each group who go to the movies at least once. So they call them moviegoers, people whom we refer to moviegoers. So someone will be called a moviegoer if he watches the movies at least once a month. At least once a month. If you go after 2-3 months and watch movie, you will not be called a moviegoer. So see, there are different age groups. So I can call the first age group as A1, the second age group as A2, A3, A4, A5, and A6. So see, 6 age groups are given. So it means they constitute all my adult population. So my sample space is adult population, age distribution for adults. So the sample space is adult population. So my adult population is divided into 6 age groups, right? A1, A2, A3, A4, A5, A6. Now at a time you can only be in one age group. If your age is between 18 and 24, you cannot be in any other age group. And if I take the union of all these, it will give me the whole sample space. So it means they give me the partition. So these age group give me the partition of the sample space. Now the question is, an adult is selected at random. Find the probability that the adult selected at random is a moviegoer. So they ask me the probability of, let's say, M. Let's say I can call M for moviegoers, right? So probability of M. Now any age group person can be a moviegoer. You can be 25 and you can be a moviegoer. You can be 54 and you can be a moviegoer. So it means this moviegoer is defined over all these, right? So this is my M. So moviegoer. So see, I got the same scenario. Now I have 6 events in my partition, A1 up to A6. Now if I write any formula, it will have 6 terms in it. So for this one, I need law of total probability. So see, if I do that, so see, they wrote everything. Let M is for moviegoer, A1 for first age group, A2 for second age group, and so on, A6 for age group. So now probability of M, because I have 6 mutually exclusive and exhaustive events, so I will depend M on all of these. M given A1, M given A2, M given A3, and so on. Okay, so here M given A1 into A1, M given A2 into A2, M given A3 into A3, and so on. 4, 5, and up to 6, because I had 6 age groups. Now these are the probabilities of AI. The first column gives you the probability of AIs, because this is the probability of age group 1. This is the percentage, so probability will be divided by 100. So you will divide 0.127. For example, probability of A1 will be 0.127. Probability of A2 will be 0.207, and so on. And the third column gives you, because this is also the percentage of moviegoers, that 83% from age group 1 go to movies. So these are the probabilities of moviegoer given that you are in age group AI. So these are the conditional probabilities in column 3. So this first one, 0.83 will be the probability of a moviegoer given that he was in age group 1. 0.54 will be the probability of a moviegoer given that he is in age group 2. So and so on. So this one will be 0.27 will be probability of moviegoer given that you are in age group 5. And this is the probability 0.109. 0.109 will be the probability of A5, and so on. Okay, so these are the probabilities of A1, A2, A3, A4, A5, A6. These are M given A1, M given A2, and so on. So we can now put the values. M given A1 was 0.83. A3 was A1 was 0.127. You see, 0.127. So you are multiplying basically A1 into M given A1 and plus. You can multiply these two columns and then add. Basically, this is the sum. We have probabilities of, in the second column we have probability of AI, third column probability of M given AI. So here I can multiply M given AI into probability of AI. So we can multiply here 6 entries and add. Or if you don't want to make a column, you can directly put the values here. See, second value 0.54 with 0.207. Third value 0.43 with 0.22. 0.43 with 0.22, 0.37 with 16.5, right? And so on. So these 6 probabilities give you the probability of a moviegoer. Now this gives you the moviegoer probability regardless of your age group. If I say that what is the probability that you are a moviegoer, it's 43.67 percentage, or 43.67% people are moviegoers regardless of their age group. Okay. What was the second question? The second question was, find the probability that the adult selected is between 25 and 34, given that he's a moviegoer. So it means they are asking me 25 is the second age group, right? This one. Between 25 and 34. So probability that he is in age group 2, given that he is a moviegoer. So you see the opposite question. Opposite question. We know M given A2 here. M given A2 is known to me, but in B part, they are asking me the opposite. They are asking me A2 given M. So how I remember it, I change it. A2 given M, I will change it according to my given probability M given A2. But once you do that, then you multiply probability of A2 and divide by this. This M is always in the denominator. So we have already calculated this in part A using total law of probability. These M given A2 was 0.54. This was M given A2, right? And this was probability of A2, 0.207. So at the top, you will only select one of them, which is being asked. But in the bottom, everything will come. So this is your Bayes law. Very easy. So this is another one. This is a solved example. I think you can do that. There are 3 companies ABC with 30, 60, and 90 employees respectively. Company A has 70% females employees. company B has 50% female employees and C has 30% female employees. Resignations are equally likely among all employees, regardless of their gender, right? Anyone can resign from the job. It does not depend on your gender, if you are a male or female. So resignations are equally likely. Anyone can resign from the job. So he said a male employee has resigned. So we got a resigned application, letter of resignation, and we saw that he was a male, right? So male is given. Given that a male person has resigned, what is the probability that he was employed by the company B? Right? So what is the probability that he comes from company B, given that he's a male? So see, there are three companies, right? Only three companies. So all sample space is divided into three companies, A, B, C. Now, there are male and female. So he said one person has resigned. So we have to find the probability that he was a male, right? This is what is being asked. So I know that this, what is given to me? Given is probability of A. There are 30 implies in A and total implies are 30 plus 180, right? Total implies are 180 implies. So if I select one person at random, what is the probability that he is from company A? It will be 30 by 180. 30 in company A divided by total 180. So 1 by 6. Probability of B. What is the probability of B? There are 60 implies in B divided by 180. So 1 by 3. And probability of C will be there are 90 implies in company C divided by total, so 1 by 2. So see, if you take the sum, it is 1, right? So your union sum of probabilities has to be 1. Now, they gave me the information about females, but asked me the question about male. So what do I need? I need probability of M given A. What is the probability that he is a male from company A? Right? So male in company A, there are 70% females in company A. It means the remaining 30% are males. What is the probability that a male selected from company B? So company B has 50% females, so it will be 50% males. And probability of male from company C. Company C has 30% females, so it means 70% will be males. So it's the opposite. Now I have all 6 probabilities. They are asking me this one. But my Bayes rule says that it is M from company B into company B divided by probability of M, right? So see, they did not ask me M before, but we can use law of total probability and calculate this separately. M from company A into probability of A plus M from company B into probability of B. You can keep that in within the formula. There is no problem. If you want to write this in within the formula, you can write that M divided by C into probability of C. Okay. So now if I put the values, M given A is 0.3, M given A is 0.3, and A probability of A was 1 by 6 plus M given B is 0.5 and probability of B is 1 by 3 plus probability of M given C is 0.7 and probability of C is 1 over 2. So you can calculate that, and after calculating this, you can put it here. Okay, and M given B is 0.5 into B is 1 by 3. Right, so this is 0.5, this is 1 by 3. So you got this at the top and denominator comes from here. But if you want to write this complete formula within here, you can do that. I think in the next slide, maybe I wrote the complete formula. No, We didn't wrote the complete. I said here this probability of M can be calculated separately. This is law of total probability again. This is the Bayes law. This is Bayes law, and this is law of total probability. Okay, so now we put this 0.567 in the denominator. Probability of M given B was 0.50, and probability of B was 1 by 3. So 1 by 3 is 0.333. So this is 0.294. All right, guys. So this is the Bayes rule, very simple rule. Let me keep this. Okay, so there is the if you have any questions, let me know. I think it's not that difficult. You just have to understand the concept. Do not whatever is given, just write that. Whatever is being asked, just write that, and according to that, try to determine your formula. Write the formula directly. Let me share the other screen, or I can share the screen. This is the screen now. Any screen will be shared. If I have some questions from the next, I think here maybe there are some questions in Bayes rule. Here you see these topics are from the Bayes rule. You can see that, right? You can see the screen. So see, if I read this question, the first one is from the topic Bayes rule. In a certain assembly plant, 3 machines B1, B2, and B3 make 30%, 45, and 25%. So you see, this is the 100%, complete 100%, right? So it means these are the partition. So if I have my complete sample space, all my products are being made by B1, B2, and B3. So all my machines, all my products are made on these 3 machines only. So it means this gives me the whole partition B1, B2, B3 because it constitutes whole 100%. It is known from past experience that 2%, 3%, 2% of the products made on each machine are defective. So it means each machine makes some defective items. If a product is randomly selected, what is the probability that it is defective? So let's say we can use D for defective item, right? Defective. So it means defective can come from each of your machines. So it can be from B1, it can be from B2, it can be from B3. So it means from here, I can write 3 probabilities. What is the probability that a product is made on machine 1? 3 machines B1, they can call them M1, M2, M3 as well. Machines, M for machine 1, M for M2 for machine 2, and so on. Probability of B1 is 30%. So 30% are made on B1. 45% are made on machine 2. It means this is the probability that an item is made on machine 2 and 25% on machine 3. So the sum is 100%, right? So this sum was 100%. So anyway, we got 3 probabilities. Next is I should know what is the probability of defective given on machine 1. What is the probability of defective given on machine 2? And what is the probability of defective given on machine 3? This should be given because this is the assumption of Bayes' law. And they are given. They said it is known that 2% made on machine 1 are defective. So 2% comes from probability defective from machine 1, 3% from machine 2, and 2% from machine 3. So these are the probabilities are defective given that a machine was known to me. Now I can write this A part. What is the probability that it is a defective item? So I can write the first A part, right? Probability of defective is probability of defective given on machine 1. You see, you don't have to remember the formula. That's what I said. No need to sit down, memorize. Just make the use of it because D depends on B1, B2, B3. So first D will go to B1, we multiply by B1. Then D go to B2, we multiply by B2. Then D goes to B3 because defective can be made on B3 and then we multiply by B3. And there is no fourth machine, so I will stop here. Now I have all the defective on machine 1 into probability of machine 1. Defective on machine 2, probability of machine 2 was 4.5. Defective on machine 3 is again 0.02 and 25% made on machine 3. Right? So this is your answer for part A. For B part, we need Bayes law. It was made, they tell me that it is made on B3. Now, what is the probability that it is defective? So they ask me, what is the probability of defect, probability of given that, sorry, what is the probability that it is made on machine 3 given that it is defective? So see, it is opposite. This one is given to me, D given B3, but they are asking me B3 given D. So it means I will use the Bayes law. In Bayes law, I will just swap them. D and B3 change their position, but then I will multiply by B3 and divide by probability of defective. So defective will come from here and D given B3 is 0.02 and B3 is 0.25. So simple Bayes law. So see, just write down whatever is given. Try to make this picture. This picture will really help. How to write the law of total probability and how to write the Bayes rule. Okay. So I hope this will help. This question from the assignment. So you can try this question too, second part of the assignment. Okay, and try this and hope you will be able to do that. Any questions? Okay, so that's it from my side. Let me stop the recording.